Yeah, so thank you very much for the invitation, and it's been wonderful to hear the talks yesterday and today. And also I want to congratulate you on this new consortium with non-Gauss, this collaboration between the different universities. So it's exciting to see that happening. What I'd like to tell you about today is work in my group towards non-Gaussian states of motion, using a Paul trap, which we've heard about this morning, but actually focusing on nanoparticles in the Paul trap. Although, as you'll see today, ions will also play a role in this story. So coming back to this theme of non-Gaussian states, as you know, they have no classical analog, and they allow us to harness quantum mechanics for both fundamental studies and novel applications. And so we've already heard talks again in the past few days on optomechanical states, because those, in particular, non-Gaussian states of optomechanical systems would enable quantum transducers, superposition states for highly precise sensing, and tests of the foundations of quantum mechanics. And so I'd like to show as an inspiration an image from Jonathan Holmes' research group from about 5 years ago, looking at a cat state for the motion of trapped ions. So clearly non-Gaussian state that they were able to map out. And so looking at this wonderful example from the ion from ion traps, you can ask now, how could we make these kind of states based on not the motion of trapped ions, but the motion of mesoscopic objects? And I'm going to focus today on levitated optomechanics. So we've heard examples of clamped optomechanical systems, or also this example from today of superfluid helium, which may be neither levitated nor clamped, but here we're going to talk about really systems that are suspended. And I want to point out 3 papers that came out about 10 years ago proposing these ideas concurrently, that really levitated particles could offer some nice advantages for these kind of experiments in the quantum regime. So when I say levitation, I'm talking about optical tweezers or magnetogravitational traps, electromagnetic traps. So anything that's going to decouple an object from its environment. And what's exciting here is that, this decoupling from the environment, it's actually enabled these systems to recently reach the quantum regime. So I would say, very broadly speaking, levitated optomechanical systems are not yet as advanced as clamped optomechanical systems in terms of how far they've been able to get into these kind of quantum mechanical experiments. But they've made a lot of headway in recent years. And so, what are we thinking about when we're talking about this decoupling? The advantage is that because you have no mechanical contact, no thermal contact with your environment, you can actually do these experiments the kind of experiments I'll describe at room temperature, rather than in a cryostat. And that if you operate under ultra high vacuum, you can take advantage of a very low damping rate. And so you have access to mechanical oscillators with very high quality factors. And finally, again, through this decoupling, you can approach coherence times that really enable the preparation, or have not yet enabled the preparation of exotic states in the quantum regime, but that we hope will enable us to do that. So let me just kind of point out a couple of highlights in bringing these systems into the quantum regime. On one hand, back in 2016, there was a direct measurement in Lucas Novotny's group at ETH Zurich of photon recoil with these particles, so a levitated nanoparticle in optical tweezers. And most recently, just last year and this year, there have been 2 really beautiful demonstrations about cooling the motion of levitated particles to their ground state. So this image is from a paper from Marcus Aspelmeyer's group that came out in Science last year, where you can see here a particle in that's held in a tweezer that's coming from above through a microscope objective, and that's coupled to a cavity, and that was cooled to the ground state. There's also even more recent work from Lucas Novotny's group cooling in a cryostat, but not via the cryostat, cooling optically. So this is really puts these levitated systems now in an exciting place where they have we can really start to say, okay, you start in this quantum mechanical ground state, and can you go from there to non-Gaussian states, building on that first preparation, that first cooling step. So these two examples, or actually all three examples that I'm referring to on this page about photon recoil and ground state cooling, these are about particles that are held in optical traps. But we're focusing actually on particles in an ion trap. And so what I'll tell you about today is silica nanoparticles, which are levitated in an ion trap. And here light is used not to trap the particle, but actually you're going to use just a little bit of light to probe the motion of the particle. So maybe reduced by something like more than a factor of 100. So the fact that we're not using light to trap the particle, that's going to help us in terms of reducing the motional decoherence in the system. And it's also going to help us in terms of reducing internal heating. So the particle is then not going to kind of heat up, even though silica is really good for keeping heating down. Still, these things can get really hot, especially under ultra high vacuum. And so that's also an advantage of an ion trap. Ion traps have extremely deep trapping potentials, as you've already heard about this morning. And they have large trap volumes, which can make it easier experimentally to capture these particles. And finally, ion traps can trap ions. So I'm telling you about nanoparticles, but what I'm going to describe to you shortly is that we'd also like to work with both nanoparticles and ions, where we see ions as a route towards non-Gaussian states. That is, ions can provide us with an auxiliary qubit system that lets us introduce a nonlinearity. So I'll come back to that later. But first, I want to be clear here that the experiments I'm going to tell you about today are not yet in the quantum regime. So in comparison to these two really breakthrough experiments that have now reached the quantum regime with optically trapped nanoparticles, ion traps offer some unique challenges in that you have a physical trap, and so that does reduce optical access, which if you're trying to cool a particle optically, makes things a bit more complicated. Also, the large trap volumes then make things a little bit more complicated in terms of optical cooling. But we've made some nice progress on this front in my group. And so what I'd like to describe to you is efficient detection as a route towards the quantum regime in these systems. So let me give you an outline now that I've tried to motivate this discussion today. So I want to start by coming back to this question about non-Gaussianity and try to tell you where we're heading. That is this vision that we have of working not only with nanoparticles, but also with trapped ions as a route to the preparation of non-Gaussian states. Then the next 3 points are all about experimental results. Although the paper on the last point is a theoretical paper, and we're just doing some experimental work now. So the first point is telling you about how we can trap these nanoparticles in ultra high vacuum for these experiments. And then the third point here is about how we can feedback cool a levitated nanoparticle in an ion trap. So this is something that we recently published. And finally, what we've been working on is showing that we can efficiently detect the position in general of a dipole scatterer, here of a nanoparticle, via a method that's known as self-homodyne. This is a method that was actually developed originally for ions here in Innsbruck, and we've now taken it and tried to apply it to nanoparticles. And then I'll try to describe to you how that current state brings us, kind of lines us up for future experiments that we hope will be in the quantum regime. So how do we see this route towards non-Gaussianity? We've heard a lot about optomechanics, and this is a Hamiltonian that you saw in Jack Harris's talk this afternoon. So this is a Hamiltonian that's describing the interaction of light and motion. Here in this cartoon, it's in a cavity where we have a light field in the cavity and the motion of a levitated particle. So we're looking at the number of photons, the number of phonons, and the interaction between the motion, B dagger plus B, that's quantized, and the intensity of the light field. So that looks nonlinear. We have then a cavity frequency in the photon, mechanical frequency in the phonon, and yeah, this is what I mentioned earlier, number of photons in the oscillator position. The problem is that the coupling parameter G naught that's parameterizing this interaction between the intensity of the light field and the motion of the position, experimentally, that tends to be quite small. And so in the solution that the approach that's been used in a whole range of different experiments is to use a strong field instead of just a few photons. And then the quantization applies then to the fluctuations of the field. But the cost is then a linearized interaction. So when you look only at the fluctuations, that is, you replace this photon operator with an average plus a fluctuation term delta A that's quantized, then you get a term that looks like the one I'm showing you here, which is a linearized term. Okay, how bad is a linearized interaction? You can do lots of nice things with it, including the kind of cooling to the ground state that I've described to you already. But this is a Hamiltonian fundamentally that maps Gaussian states to Gaussian states. So if you started out with a Gaussian state, which seems reasonable that you would, you're not going to be able to get out of that space. And so to make non-Gaussian states, we need to introduce a nonlinearity. Where is that nonlinearity going to come from? So I started doing these experiments motivated in part by a paper that came from Annika Planzo, Oriol Ramirez-Art, and Ignacio Sirac, and that I really got into discussing with Oriol in particular when he came to Innsbruck and started a position here. And so this was a paper in which they had outlined a theory proposal for how to use an atom or an ion to assist optomechanics in order to prepare these non-Gaussian states. And so, we had experience with ions in particular. And so when we tried to take this proposal and interpret it in our experimental world, this is what it looked like to us, the idea that we would take the kind of calcium ions that we already knew how to couple to an optical cavity. And that's not an optomechanical coupling. This was a coupling looking at the interaction of the electronic levels of the ion to an optical cavity. So this is a coupling between the atomic dipole and the cavity field. On the other hand, we would then introduce this optomechanical system, the nanosphere, and we thought that we could then use the shared coupling to the motion to the cavity field here to then assist to then essentially provide this assistance that was proposed. So this is, again, this concept that's been proposed in the paper. The paper is more agnostic about it, so it doesn't matter that it's an ion in the paper. It simply matters that it's a two-level atomic system. And so I want to kind of summarize the proposal that was made at the time. I've written down kind of the key Hamiltonian from that paper, where what we see here is the photon energy. So there's a detuning here. We're working in a rotation frame. We have then the nanosphere phonon here, that is the motion of a particle. And now there's a coupling here between the photon and the phonon, and we see we have that's now enhanced via this cavity drive. So again, we're going to use this trick of driving with a classical field, and that's what I've now illustrated in the cartoon on the right-hand side below. And now also in this Hamiltonian, you have an ion. And so the ion is also going to couple to the cavity field, and it's going to couple not optomechanically, but as a two-level system. And we can also drive the ion separately with a laser. So now there's two purple arrows in this little sketch on the lower right-hand side that are indicating these two different classical drive fields. And then there's an auxiliary term. So in this Hamiltonian above, I've written an additional auxiliary Hamiltonian, which I've now written out here. And so the key here is basically now to drive the cavity with a second frequency. So I've now indicated two different frequencies that are driving the cavity. So there's two different frequencies interacting now optomechanically with the particle. And so what this proposal shows is that you can prepare, you can look at in a dissipative regime at the states that are prepared. And it turns out that when you consider it as a dissipative system, that is, you simply turn on these different drives. In the right parameter regime, you can find two steady states. The ground state, so here I'm labeling G and E, the two states of the particle, the ground and the excited state. and 1 and 0 are then the whether you have 1 or 0 phonons in your system in your mode of motion of your optomechanical system here of the nanosphere. So the first state, this is the interesting one, right? This is a superposition here. So where we have G1 plus E0, this is the non-Gaussian state that we'd like to make. And the second state is really boring. It's a ground state. But those two states are going to be degenerate to start with. But it turns out, again, from this theory proposal, that you can lift that degeneracy in a handful of ways with autonomous spontaneous decay, with decoherence from the nanosphere, but also this additional coupling to a second cavity mode, this second auxiliary Hamiltonian that's driven with a blue detuning from the frequency of the cavity. That's going to lift the degeneracy. So the concept would be to drive the system with a handful of laser fields and try to engineer the dissipation so that this first state, the interesting non-Gaussian state, is the one that predominates, even if it's not 100% prepared in that state. Yeah, how would you read out your nanoparticle if you were able to generate this state? The proposal in this paper, and also that goes back to an earlier paper, is about doing time of flight tomography, in which one can map quadrature phase information of the particle's motion, that is, so onto the sphere and then release the sphere from the trap, and a position measurement in the cavity then determines this momentum. But you could also think about here harnessing the ion, that is transferring the state of the nanosphere to the ion, and then performing quantum state tomography on the ion. It's not something that I think we've thought about too carefully at this point, because right, we're simply a long way from those stages. So that's the vision. Why would we like to use ions here in particular as auxiliary qubits? Well, so if you listen to this morning's talks, hopefully you're already sold on what wonderful quantum systems ions are. Let me just remind you of some of the highlights that you've heard. So they're a highly controlled two-level system where you have opportunities for both hyperfine and optical qubits. You've heard about coherence times that go up to an hour in Q-on-Kim's system. Internal state readout that can be done with very high precision via electron shelving. And what you heard about today is that you have this opportunity for coupling between the qubit state and the motional state. And finally, that you can manipulate the states of these ions in a deterministic way with very high fidelity, coherently through laser or microwave operation. And so these ions, it's been clear for some time that they're very well suited to optomechanics. And so you saw some examples of recent ongoing work in this direction today. But I just want to point out that this kind of goes all the way back now more than 2 decades. Here's work from Dave Wineland's group, kind of these first glimpses of looking at Fock states and squeeze states of trapped ions, again, back in 1996. So it's clear that you can prepare interesting motional states of ions. And then there's a cavity that goes into this story. So we're going to want to couple ions and nanoparticles to a cavity. And that's something that we've done in our research, but also that's been done in other groups. So cavity coupling to the qubit transition, to this electronic transition of an ion, has been demonstrated. It's at infrared wavelengths, which is really nice, kind of experimentally, in terms of frequency that's that transmits well through fiber, that's easy to work with. So that interaction, again, that I wrote down earlier between the light field and the two-level system, in a cavity, this is the Jaynes-Cummings interaction. We've looked at it, for example, as a way to transfer a quantum state from an ion to a photon. So this is a photograph of a system that we've been using for several years for experiments with ions and light and single quanta. So what you see in the middle is an ion trap, a linear Paul trap, and then there's an optical cavity that allows us to couple single photons to those ions. But we've actually just heard about cavities that are much smaller, that are based on optical fibers. And those kind of fiber cavities have really an advantage here as well. In particular, they offer us a route to boost the coupling strength between the atoms and and the photon. So here now we're not talking about the optomechanical coupling, but rather the coupling here in this Hamiltonian between sigma plus and A and sigma minus and A dagger. And so that coupling strength, that's about the getting a really small mode volume for this interaction. And so it helps to have a really little cavity. So this strong coupling, that is, if you can get your coherent coupling rate to be larger than any of the other dissipative rates in the system, this has not yet been demonstrated with single ions. It's been demonstrated, for example, there's work going on in Gerard Rempe's group now with neutral atoms. Back in we also did this in Jeff Kimball's group some years ago. So this single atom strong coupling is something that's been shown, of course, also with in the microwave regime, but ions a bit more challenging, in particular because of the trapping potential. And so it's, again, difficult to get this small mode volume and still have a nice stable trapping potential from ions. But fiber cavities, I think, are the best route towards this. This is a picture from a physical review letter from Michael Kohl's group, picturing, and yeah, it's a composite picture. So there's, on one hand, the picture of the ion trap electrodes above and below, and the fiber cavity, sort of a shadow of the fiber cavity on the left and right hand side. And then inside is a picture of a little ion, a fluorescence image from my camera. So they're able to couple ions to these fiber-based cavities. And because it's such a small cavity, it lets you enhance that interaction. This is a photograph of a fiber cavity setup that we've built up. We're working on coupling ions to a new fiber-based system. So we've gone through a couple generations of these setups now. I think we're optimistic that we'll have some results soon with this setup, but still it's work that's underway. Okay, strong coupling on the horizon. So we have a route with ions, not only to work with them as beautiful two-level systems, but also to couple them to optical cavities. I've already argued to you that we have a nice deep trap confining potential with ion traps, then that allows us to decouple from optical fields. And it also provides some possibilities for novel cooling methods. So the cooling methods that I'm going to tell you about today are about using optical fields, but I was also part of a proposal that you can see here on the lower right-hand side for cooling via electrical field pickup. And that comes back also to some proposals that were made with for trapped ions several years ago about these cooling methods as well. And finally, you could imagine also that if you have nanoparticles and ions in this kind of a hybrid system, you could use the ions to probe some aspects of the nanoparticles as well. Okay, this brings me to the second part of my talk. So I've tried to motivate why we're interested in trying to put not only a nanoparticle in a cavity, but also an ion in a cavity and couple them via the cavity field. And now I'm going to try to tell you about how far we've gotten in that experimental work. And so we started at the very beginning. This is work that we started back in 2017. So it's been about 4 years now working in this direction. And we needed to get some nanospheres and we needed to trap them. And in particular, these experiments, we needed to do them in ultra high vacuum. Again, in terms of our long-term goals of working with quantum states. And that may sound, yeah, not particularly challenging to those of you, for example, from a background of working with cold atoms or ions where it's just what you're used to. But in terms of the experiments that have been done so far with nanoparticles, it tends to be that the methods for loading nanoparticles into a trap, whether it's an optical or magnetic gravitational or even a Paul trap, have been relatively dirty from a vacuum perspective. And so when we thought about how we wanted to do this in a way that would be consistent with ultra high vacuum, we turned to recommendations from Marcus Arndt's group in Vienna, which had used laser-induced desorption. And then we kind of advanced this a bit more with the trap particles. So let me just outline for you this concept of laser-induced acoustic desorption. This is a picture of, some nanoparticles. I think there's a square that disappeared here where they're supposed to be evaporated onto a small piece of foil. So we take a small piece of aluminum foil, the nanoparticles are evaporated on the foil, and then we come with a pulsed laser to one side of the foil. So that laser is focused down onto where the picture of the foil is supposed to be. And then there's an acoustic wave that's generated in the foil. And so particles are desorbed from the other side of the foil via this acoustic wave and are launched to the direction of our ion trap. And so we can check that by taking some microscopy pictures. And here's a picture where we just we put the particles in the foil and look at, check to see that there actually are particles that have been absorbed onto the foil. And then after we use this pulse laser to desorb the particles, we verify that the particles are in fact not there anymore. Okay, so let me just show you that these are relatively simple experiments in a vacuum system, where if we zoom in on the vacuum system, you can see now what's a quite simple Paul trap. I'm going to zoom in now a final time here on the trap itself. So circled in red here, this is our linear Paul trap. And so I've labeled here on the right-hand side in this schematic, the AC electrodes and the DC electrodes. I will probably tend to call them RF electrodes because for trapping ions, you drive them at radio frequency. But here we're driving them at lower frequencies. So something like, say, tens of kilohertz, due to the different charge to mass ratio when you're talking about nanoparticles versus ions. So in order to have stable trapping of these nanoparticles, we drive at lower frequencies than you would for trapped ions. So there's an AC drive frequency. There's also DC electrodes above and below, and those provide confinement in a third direction. So the AC electrodes provide a two-dimensional pseudopotential. The DC electrodes of this Paul trap provide a third dimension of confinement. So the harmonic potential here is just to remind you that what we have is a harmonic potential in 3 dimensions. And we end up with secular motion of the particle at the frequency of an effective potential in the kilohertz range. And then there's also what's known as micromotion in these Paul traps at the original drive frequency, which you can take some steps to suppress down to minimize. So that's the Paul trap. And now here, where you circled in blue, you see this foil that I've described to you that we've evaporated these little nanoparticles onto. And the tube that the foil is kind of inserted into, this is a hollow metal tube. And so we have a pulse laser that's coming through the tube from the left-hand side, and that we use to desorb the particles in the direction of the trap. Okay, so that's how we're going to get the particles into the ion trap. But you might be worried about something. In particular, that this trap is a harmonic potential. And so, we have some conservation of energy, and the particles are going to roll into the trap and roll in that potential, and they should just roll right back out again. Why can we avoid that? So let me kind of show you a little cartoon here of this laser. Maybe I'll go back here. How do you avoid that with an ion trap? Why don't the ions roll back out again? It's because actually you will only ionize the atoms when they're in the potential already. So it's a nice trick where you can have neutral atoms and you ionize them when they're already in the place where the potential is. They don't yet see the potential, you ionize them, and then there's a potential. But here, we're not going to create the nanoparticles only in the trap. So we need to use a different trick. We're going to turn on the trap only as the nanoparticles cross it. And that's what you're going to see here in this little animation. So here comes the acoustic wave, the particle is desorbed. And we only turn on the Paul trap once the particle's in it. The particle somehow got displaced here, so it should have been in the trap, and then it would have stayed there. So we only need to we're only turning on these electrodes when the particle is confined. And that's what you see with this Paul trap voltage that's turned on at the right time. Yeah, I just realized before, when I was checking my slides this afternoon, that this movie somehow seems not to play. And I think it's a difference between my Windows laptop that I usually use for talks and this Mac. So unfortunately, I can't play you this video, but what you would see is that you would see this particle oscillating and then get trapped pretty quickly. So you would just see this sort of flash as we pulse the laser, and then a particle that becomes trapped actually quite quickly, because we're doing it first in the first video at a relatively high pressure. And then we have a different version. So we did a lot of analysis of this loading at pressures here that are not in ultra high or even high vacuum, but something like 10 to the minus 3 millibar. And we analyzed the loading efficiency. We saw that it agreed nicely with our simulations. And we understood that we could get actually a loading efficiency of kind of loading a particle about 1 out of every 2 times that we tried to do it. So it's pretty close to push button where you try to load a particle and then you have one in your trap. And we understand that the speeds of the particles, it's nicely, what we see is that this efficiency is independent of the pressure. So even as we reduce the pressure of these of our vacuum chamber, we still have no problem loading these particles. This is a picture now of how we can see these oscillations of the particle damp. So we load the particle, it's oscillating within this trap potential, and then it becomes damped due to background gas cooling, and which we've also analyzed. So we understand it, but this is a bit of a problem that we relied originally on background gas cooling, because for ultra high vacuum, of course, you're not going to have so much background gas. So the second video here that I can't show you, it's showing a particle getting trapped at much higher pressures or lower pressures at now in high vacuum of 10 to the minus 6 millibar. And it's a quite slower process, which is why it's actually speeded up in this video so that it doesn't take a half an hour, which is the actual length of the video. And so that indicates that we would have serious problems trying to do this if we wanted to work, say, at 10 to the minus 10, 11 millibar. Yeah. So what we've done instead is we're using now buffer gas cooling. So we've switched to an ultra high vacuum chamber, and we load particles, and we then pump in argon or nitrogen, and we use the argon or nitrogen to buffer gas cool the particle, and then we pump out that gas. And we can do that quite well. So that allows us, so the first picture you see is simply an oscillating particle where we didn't, it was our first kind of trapping at ultra high vacuum, but we weren't damping it. And more recently, what we've done is pump in these gases in order to damp them. And we see that we can also pump them back out very effectively. So then we can work at ultra high vacuum with these particles. Great, so we have particles. What are we going to do with them? Well, we'd like to get them colder than we're getting them simply by background collisions with gas. So that's going to get us to room temperature. But how can we really get them to the bottom of this trapping potential? Well, first of all, of course, we're not the first ones to want to cool these nanoparticles, and that's been going on for now more than a decade. So there's examples, for example, early work from Mark Raisin's group looking at feedback cooling, otherwise known as cold damping, of, here you see an optically trapped particle in this image. Also, what was done shortly afterwards was parametric cooling. And then there's been several examples as well of cavity cooling of particles. So a handful of different methods that have been used so far to cool these particles. And I should say that in terms of reaching the ground state, this has actually now been done with two different approaches. So feedback cooling and cavity cooling. This is now, again, this quantum regime. So in a Paul trap, what's been done so far here? Well, on one hand, people have looked at single particles using parametric feedback on the electric field. And there's also been cooling the cavity optical potential. This is the third reference on the right-hand side that I've left ungrayed out here. So you can see a picture of kind of oscillations of a particle. This was worked on in Marcus Arndt's group. So either electrically or in the optical potential, but actually it wasn't relying here on the ion potential, but rather sort of the optical field inside of an ion trap. And so what we've looked at, and what I'll describe here, is both electrical and optical feedback cooling in a Paul trap potential that was done under high vacuum. So this is the kind of setup that we can use to cool these particles. Again, it's a schematic of an ion trap. So what you see are these electrodes. It's not all of the electrodes for an ion trap, but I'm just indicating the confinement of these particles here. And then you see a picture of the particle. And this is a summary of how we can detect the position of the particle. So what we're doing here is, on one hand, we're sending in a probing beam from the left-hand side. And this is now focused down, not too tightly, in the trapping region. And then the particle is scattering light, and the scattered light is position dependent. And then on the right-hand side, you see some balanced photodiodes, so a pair of photodiodes. So the light that's reaching those photodiodes is from both fields. It's from the original field, part of the field that didn't see the particle, but it's also the position dependent scattered light. So that combined information then allows us to extract the position of the particle. So therefore, we're getting a position signal based on the difference of those two balanced photodiodes, and that's a signal in one direction. And we can duplicate that in 3 directions if we want. So here's a picture where now we see the whole image of the Paul trap in vacuum. And then what you see below, so you see onto the right-hand side an output path of this Paul trap. And then you see 2 different pairs of these balanced photodiodes. One is used for detection in the along the z-axis. The second is used for detection along the x and the y-axes, where these are at different frequencies due to the different trap frequencies of our ion trap. So we can spectrally separate out the motion in all 3 directions of the particle. And so that's what's done first with kind of feedback electronics to separate out the particle. And finally, you see also a third pair of these balanced photodiodes for monitoring the in an out of loop scheme for monitoring the position. Okay, so this is already describing what we see here. So this is a picture here of the power spectral density from the different modes, looking at what you would see for both the Z and the X and Y. So I've just described, it's depicting what I've already told you, that we actually have 3 non-degenerate modes of motion here in the kilohertz regime. And then we're using feedback here. This is with a red pitaya and using a open source purple software. That's so we're taking information about the particle's position, and we're essentially just taking the derivative of that with this FPGA system. And now we have a feedback signal that's just just pushing us back based on the derivative of the positions. That's giving us the velocity. And we're summing those signals back together because they're at different frequencies. And now we do 2 things with that feedback. We either use optical feedback or we use electronic feedback. So one option here is that we can, on the left-hand side here, we can feed back to a cooling laser, which is at a slightly different frequency at 1064 nanometers. And we can superimpose a potential from a laser on top of the trapping potential from the ions. So we have a hybrid potential, and then we're sort of turning up and down that trapping potential of the laser in order to make things deeper or shallower for the ion, depending on its motion. So that's one method of feedback. Another method of feedback is purely electrical, to take advantage of what you see on the right-hand side, these feedback electrodes that are sketched in here. So we can do one or the other using the same signal. And then the question is, does this work? Which we're going to monitor using these photodiode detection methods. Okay, so this is the plot to show you that we can indeed cool the particles. So above you see these, the power spectral density of the particle. So this is now just taking the signal that we have from these detectors, looking at it on a spectrum analyzer. We can separate out the different motional peaks, and then we turn this cooling on, and you see much narrower spectral densities that indicate that the motion is being cooled. The results I'm showing you here are for optical cooling, so feedback to the laser, but the electrical results are very similar. So it's what we're limited by is the detection mechanism, and the feedback we can really do one way or the other. It turns out that both the feedback mechanisms that we have, they overlap with all 3 axes. So it's a single feedback mechanism. It's either a single laser or a single, it's a pair of electrodes, but a single electric field. But the point is that both the laser direction or the field, electric field compensate, or the field generated by these electrodes, those have an overlap with all 3 axes. And so they allow us to talk to all 3 axes at the same time. Again, because we can spectrally identify the different frequencies. Right, so here are the temperatures that we cool down to, something like in the range of tens of millikelvin. So we started at 300 Kelvin, we're down in about 10 millikelvin, so it's a big step, but we're still talking basically about something like 10,000 phonons, so not yet at the quantum regime, they're not yet near the ground state here. What does that mean as a function of pressure? So we did this cooling for different background pressures, where you see here, so 3 different theory curves and also 3 different sets of data. So the data is, there's 6 sets of data, both electrical and optical cooling at the 3 different pressures. And so why did the theory curves go down again and then go up again? Whoops. So on one hand, they're limited. On one hand, you're limited because you're not feeding back enough. So the x-axis is essentially the gain, the feedback gain. So as you crank up your feedback gain on the x-axis, you increase your feedback signal, you cool your particle better and better, more effectively. But at some point, as you keep cranking up your gain, there's a back action. And then your curve starts to go up again. That's what you see most clearly with the light pink, the lowest curve. It's a bit harder to see with the other curves, but they also turn a corner and start heading up as back action kicks in. So, right, what are actually the theory curves? This is a model from a paper from the Novotny group. And we can separately measure all these different terms. So we're not fitting this here. We're putting in parameters that we've measured separately. For example, the background gas damping rate, the cooling rate that we extract from the line width of the power spectral density, the power spectral density of the in-loop motion, which gives us a detection, so it's detection noise. And so we were happy to see the agreement for the first 2 pressures, although it definitely seems that there's clearly an offset for this lowest pressure. We suspect that this was about radio frequency noise of the Paul trap, but we need to investigate that further. And I think, yeah, it sort of shows you that things are going to get more interesting as we push the system down to lower pressures. These were experiments that we did only, at pressures about 10 to the minus 7 millibar, because we weren't yet working with our ultra high vacuum chamber. So I've shown you electrical and optical feedback cooling, and both of them have their advantages. So on one hand, because electrical cooling acts on all particles at once, it would let you, you can just talk to all of the particles in your trap and get them all cooled together. But it can be nice to have targeted addressing. For example, you can imagine the hybrid system that I'm describing to you, where you have a nanoparticle and an ion, and you only want to cool a single one of those. Or you can imagine in the second sketch that you see here, a little diamond, which is supposed to indicate like a nitrogen vacancy center or some other defect that's embedded in a particle. So that would be a kind of particle that might heat up a lot by itself and actually just kind of evaporate in UHV if you decided to put too much laser power there. But instead you could cool a silica particle, which would be much more amenable to cooling in ultra high vacuum, and use sympathetic cooling in order to cool your more delicate opaque particle. Okay, but how do we push these temperatures down from the 10,000 phonons that I'm describing you to really work in the ground state? On one hand, the slope on the left-hand side, this is about the temperature, about the pressure. And so if we lower the pressure, well, as you can already see convincingly by these 3 orders of magnitude, if we drop the pressure further, that's going to bring down the slope of the theory plot here on the left-hand side, and hopefully also of the data. And so we're now, again, as I mentioned, working at pressures that are more than 3 orders of magnitude lower. So we're looking forward to retaking this data. How do you bring down the right-hand side? This is this back action story. There, you need to have lower detector imprecision. So, for every disturbance of your particle, you want to be getting your money's worth in terms of actually having an effect. So your detector should be effective, and that's what I'm going to talk about in the last part of my talk, how we can do efficient detection, even in the system where we don't necessarily have a great numerical aperture to collect as much light as we want to collect. Okay, as I mentioned at the beginning, this goes back to work with trapped ions that was done here in Innsbruck and Rainer Blatt's group. And so the reference here and the picture, this is from a paper by Pavel Bushev and colleagues. And so what do you see here? This is a barium ion that's sketched in this trapping potential. And so the barium ion is fluorescing. And the fluorescence goes into 4 pi. But basically in this drawing, you can see that the fluorescence we're interested in is going in 2 directions. Either it's going directly to the right-hand side, or it's going to the left-hand side, reflecting off a mirror, and then going to the right-hand side. So the fluorescence that's collected in these 2 PMTs that are illustrated, so these 2 photomultiplier tubes, this is coming either directly from the ion or from the ion, but reflected first off a mirror. So there's interference between these two paths with and without the mirror. And that interference, so that means that the motion of the particle is going to modulate this. So that's going to, the modulated fluorescence will provide us information about the position of the ion. And in this paper, what the authors did is then they took this signal, and again, as I've shown you for this kind of feedback cooling that we've done more recently with these nanoparticles, you then take the signal about the motion, you apply a phase shift, and then you use that to feed back, in this case, to the trap electrodes, and they use it to cool the particle. So yeah, this is then, there have been some really nice recent extensions. So Lucas Slajička, I think he's actually here. He's now at Olomouc, but this is when he was in Rainer Blatt's group, and he did really nice work on thermometry. So understanding the temperature, how can you predict the feedback cooling parameters? And even more recently, Giovanni Torchiari has looked at the single phonon sensitivity of these systems. So why are we calling it self-homodyne here? The idea is that it's now so the homodyne aspect is this interference of these two different light paths. And the self aspect is that this is from the particle itself, that it's the emission either to the left or to the right. Okay, so this was for ions. Can we apply this method to nanoparticles? And is it going to be useful for us? So yes, the method has nothing to do with ions as charged particles. It's valid generally for a dipole scatterer. And so below here, the first sketch that I showed you, this is an illustration of the concept. This is just describing the image of the particle here. So this is describing, sorry, that you should look first at the red. So the red is the actual particle. It's being illuminated by an addressing beam. And now you see the red signal that's reflected that goes to the left, reflected off the mirror, comes back as the blue signal. And then you see an image of the particle that's generated. And that we can compare with more standard detection methods. For example, the method I described to you earlier, where forward scattered light interferes with an addressing beam. Or you can also look at backward scattered light, which can interfere with a local oscillator as well. And so, yeah, this is to remind you that it's actually the forward scattered method is what I've shown you earlier. And in comparison to these other methods, self-homodyne has some really nice advantages. In particular, this secondary dipole image matches the wavefront of the primary field. So you could either use a curved mirror, or maybe more practically, you could use what's shown here in the sketch, a lens plus a flat mirror, but you're going to reproduce the idea is that you're really imaging the particle so that you have a matching wavefront in contrast to the local oscillator, which is not going to match the wavefront of the particle emission. You have a coupled system which emits light in only half the solid angle. So that is right, it's clear that you can just collect it with one set of detectors, and you have the freedom to choose the angle between the mirror axis and the addressing beam. So that kind of gives you more flexibility in your experimental system. Yeah, what I'm showing you here is a theory result that in work led by Giovanni Torchiari that was about understanding whether this self-homodyne method, can offer an advantage. That is how it compares to these forward and backwards methods. So what's being plotted here on the x-axis is the numerical aperture of the detector from 0 to 1. And on the y-axis is this inverse imprecision in detecting the particle displacement. So if this is lower, if the imprecision is lower, it means this inverse imprecision is higher. And that means that we increase the visibility of the thermal motion. Okay, so what do we see here in this plot? It's a bit complicated, so we'll start with the black line. And this is describing the self-homodyne along the z-axis in this diagram on the left-hand side. So this is self-homodyne with an ideal detector, and it shows that as the numerical aperture goes to 1, we can go actually all the way up to 1 with this inverse imprecision. Then we look at blue, which is now still the self-homodyne, but with a discrete pixel detector. So we factor in some realities about this detector. And we also compare that with the backward detection, which is dashed. And then here we look at some other axes, the y and the x axes, again, comparing self-homodyne with these forward and backward methods. So yeah, the message here is to say, yes, the self-homodyne does offer certain nice advantages. And in particular, so the plot's going all the way up to high numerical apertures, but you can get a particularly good advantage for the lower numerical apertures, where in our own experiments, we're kind of limited to those ranges. So we have some preliminary experimental results, which I'm going to show you quickly to wrap up. This is a different trap, but same concept, a linear Paul trap. We have then a 2-inch mirror on a piezo stage in our laboratory that's outside of the vacuum chamber. And so first what we do is we scan the mirror position, and we can find a photodiode signal that's oscillating. And this is just giving us a length measurement. So it's kind of helping us understand, as we scan the mirror position, we can then kind of calibrate then its motion, because we see that it has to correspond to half of the wavelength of the light. So it provides us with a calibration for the particle motion. And this is an example now of, we can look as a function of time and look at these particle oscillations. And we see now that the really fast oscillations are actually at this micromotion at the trapping, at the frequency we apply to the trap. And the slower oscillations are then the motion that's more interesting to us. And this is now, if you look at the power spectral density with the spectrum analyzer of this kind of a trace, you can see, why do you see a lot of peaks? It's because we have different motional modes. So here we're looking at, essentially we're looking pretty much at 2 modes. So that's why they're sort of in pairs. These are in 2 different, in a plane. And we can see both the secular motion as peaks and the micromotion here. Yeah, so we're still analyzing data about this, but this is kind of preliminary work where the contrast here on the power spectral density measurements in comparison to our earlier results is very promising. Right, so we're working, as I mentioned, on analyzing this cooling based on the self-homodyne method and on comparing it with theory. The next step would be implementing it in our ultra high vacuum setup, where we've done some calculations. We think it should let us get to the ground state, given the much lower pressures in that setup. And one interesting outlook is to measure the variance of the position by measuring the particle not at an antinode, but in fact positioning the particle at a node of the field. And that's work that Giovanni Cerchiari has been thinking about as well. Okay, so that was a story about cooling and about efficient detection. And on this last slide, I want to try to tell you where we're heading in a broader sense. So I've just told you about experimental results with nanoparticles, but we're also working on co-trapping nanoparticles and ions in ultra high vacuum. And that is what we're trying to do, is to drive the linear Paul trap at 2 different frequencies. Okay, here you see that they're both marked as radio frequency, but yeah, the lower one is kilohertz, and the higher frequency is megahertz. So essentially, we drive a trap at a frequency that's talking to the nanoparticle and a frequency that's talking to the ion. And these 2 references here are proposals for how to do that in a way that satisfies the stability criterion for both particles. We haven't yet successfully trapped the particles. We're hoping to see some results there soon. So fingers crossed, it's an exciting time in the lab these days. Meanwhile, we're also working on optical cavity integration. Florian's picture, I think I didn't yet get a chance to put it at the end, but Florian joined us very recently, and he's working on integrating an optical cavity with a so-called wheel trap. This is a kind of an ion trap, a linear Paul trap that was developed at NIST in Boulder, and that we've adapted for using in some of our in one of our other experiments. We like this trap also for optomechanics because it's very compatible with this kind of small mode volume and good optical access. Right, so to wrap up, I've tried to convince you that levitated optomechanics, and in particular with an auxiliary qubit, provides a promising route for creating non-Gaussian motional states. It's not going to happen tomorrow or next month, but it seems like there's a lot of momentum in the field on levitated optomechanics. And in particular, we think that by using an ion as an auxiliary qubit, we can harness a lot of the experience, not only that we have with ions, but that's really been developed, this toolbox that researchers have been developing for several decades on manipulating these states. So we've cooled the motion of a levitated particle with both electrical and optical feedback to the millikelvin regime. We see some routes for squashing that down a lot more. And we've proposed a method for efficient detection, and we've performed some initial experiments that I've described to you. So here's a couple of the pictures that I showed you today, and let me also show you a picture of the people who've been doing this work. So Lorenzo and is a PhD student on the project. Dimitri is a postdoc. Pau and Matthias, so Pau's a former postdoc, Matthias is a master's student, and they worked on the first project. Max Moisberger is a master's student, Katharina Heidegger is also a master's student. The two of them, the two of them have both worked on the second project, and Giovanni and Rainer Blatt were collaborators on the self-homodyne. Thanks.